So in this video, I will be briefly addressing the two probability distributions, hypergeometric probability distribution and then Poisson probability distribution. So in binomial probability distribution, we know that the probability of success does not change from one trial to another. So basically, when you do an experiment with replacements, that's the idea, that probability would not change from one trial to another, right? For example, you draw a card and you put the card back in the box, and then you draw another card. So that falls under the binomial category. Because every time, let's say when you draw a card and you're just recording its color, so the probability that the color being red, if that's what you are trying to count, how many cards would be red color, that's your success, right? So then every time when you draw a card, the probability that it would be red is going to be the same because you're putting the card back in the box. So the hypergeometric is the other side of the experiment. So you're drawing a card, recording its color, but you're not putting the card back into the box. So if you're running an experiment without replacement, then you know from one draw to another, the probability is going to change. So drawing a card, recording its color, let's say that you're recording whether it's red, and then you set the card outside, and then you draw another card and see if it's red again. So when you check that, the probability that second card be red is going to be a conditional probability, and it's not going to be same as the previous time, right? So in that setting, we have to group that kind of experiments under hypergeometric probability distribution. So even this is true for selecting people, right? So if I have a finite population, for example, my class, I have 40 students, and if I'm drawing students in, let's say I'm selecting students to be included in a committee. So I need to choose 10 students out of my 40 students. So I'm selecting one student to be included in the committee. And once I select the first student, that student is already included, right? So then when I'm selecting again, I only have 39 students in the pool, right? So then the probability is going to be changing from one selection to another. So that's the difference between binomial to hypergeometric probability distribution. And the rest would be the same idea. You should be drawing n amount of things, or you should have n trials in the experiment, and only two possibilities you should occur in each trial. Those conditions, those requirements would remain the same for a hypergeometric probability distribution. So if I just briefly list the requirements in trials, each trial results two possible outcomes. Success or failure, and we are counting, our variable is to count the number of successes. Variable defined is the number of successes. And then the fourth one, which makes this distribution different from the binomial, is that probability of success. Changes from one trial to another. Okay. So these are the requirements for any experiment or a random variable to be hypergeometric. And if that's the case, we can use the hypergeometric approach and compute the probability distribution. And the thing is that this can only be applied for a finite population, because when you try to formulate the hypergeometric probability distribution and get the table done, you need to know the population size. Without knowing the population size, you cannot use this approach. So for a finite population, a small enough population, we can most certainly apply this concept. Okay, so the information we need, like for binomial, we needed two information, right? N, the number of trials, and simple p, the probability of success. For hypergeometric case, we need different information. We need three different information in order to apply hypergeometric approach. So hypergeometric variable, you need the population size, capital N, and S stands in this setting the number of successes in the population, and then simple N, the number of trials. So this is population size. And this is number of trials, so the sample size. Okay, so if you happen to know this information, you can easily use Excel and get the probability distribution done. Okay, so I'm going to explain this idea using an example. So let's look at an exercise from your textbook. Question number 27. It says a CD contains 10 songs. That's the total amount of songs. 6 are classical and 4 are rock music. So two different kinds, right? And then in a sample of 3 songs. So now you're drawing 3 from the 10 total list. What is the probability that exactly 2 are classical? So you are drawing 3 songs, one after the other, and you're counting out of those 3 how many would be classical. So that's what your variable is. So 10 songs total, that's capital N, and then we have out of these 10 songs 6 classical and 4 rock. And what you do is you draw 3 songs and then count. So you can easily see that this is without replacement, right? You're just selecting one song randomly, check whether it's classical or rock. And then once you know whether it's classical or rock, that means you have 9 songs left in the list, right, to decide. So again, selecting another song out of that 9, so and so. So the probability that the next song will be classical is going to be changed from the first probability. Okay, so you draw 3 songs and then you count. That's what you do. Count number of classical songs. So this is actually your variable. According to the question, you have to actually decide what is your variable. So if you're counting this classicals, that means classical is the success. If you get a classical song, it's the success, and if you get a rock song, that's, you can say in general, that's the failure. Okay, so 2 possibilities, and then 3 is going to be the number of trials, n, and we have n, and if we are counting the classicals, that is our success. So 6 is going to be S, capital S. So those are the information we need. Capital N, capital S, simple N. So once again, total number of songs is the population size, capital N. So N is 10. And then we are counting according to the question. If I go back to the question, it says, what is the probability that exactly 2 are classical? So you're interested in calculating a probability about how many classical songs that you would get, right, out of those 3. So that's why we decided, okay, having a classical song, selecting a classical song is your success. So in the population, out of all those 10, 6 of them are classical. So capital S, number of successes in the population is 6. And then how many you are selecting from the population? It's 3. So that's your number of trials. So we are going to carry these over to Excel. Megastat, probability, discrete probability, hypergeometric, 10, 6, and 3. So our goal is to get the complete probability distribution. So out of these 3 selected songs, we are counting how many would be classical. So the possible values can be 0, no classical songs, 1, 2, or 3, right? So we look at the complete probability distribution by completing this step. Okay, here you go. So this is the complete probability distribution of the variable number of classical songs. And the question is actually addressing one of them, right? Just one of them we need to figure out. So what's the probability that exactly 2 are classical? So all you have to do is you just read this one. The probability that exactly 2 will be classical is 50%. So there's 50% chance that exactly 2 songs will be classical when you select 3 songs out of a total of 10 songs. That's the way you approach hypergeometric probability distribution.